So let us discuss the principle of absorption spectroscopy. When a sample containing molecules and atoms, they are being excited with light photons. Uh, and light photons are basically, as I explained in the previous class, the electromagnetic radiations are um, an EMR radiation is created when a subatomic particle like an electron is excited in an electric field. When they are excited, they create an oscillating electric and magnetic field perpendicular to each other, and they carry with them packets of energy. Those packets are called as photons. So when we have a sample containing atoms and molecules, these are excited by certain radiation, certain region of electromagnetic radiation. Then the atoms and molecules present in the sample, they absorb these light photons, and upon absorption of light, they got excited and they transfer energy to their outermost electron, and these electrons are promoted from ground state E naught to E1 or maybe to E2. In this promotion, they absorb. In this promotion, since they absorb energy, so the wavelength corresponding to that particular energy are being missing from the spectrum, and therefore we can say that absorption occurs at a characteristic wavelength. This is basically based on the report of that German scientist G.R. Kirchhoff, who reported in 1859 that each and every pure substance has its own characteristic spectrum. So similarly, each and every sample having atoms and molecules, they have characteristic wavelength value of radiation that they absorb, and that characteristic wavelength is then goes missing from the continuous bright spectrum, and the amount of light which is being absorbed is controlled by, or I should say it is governed by, the famous Beer-Lambert's law. And Beer-Lambert's law states that the absorbance is equal to epsilon C and L. This is basically absorbance is proportional to this is basically absorbance is proportional to C, the concentration of the sample, because as we have more concentration, we have more atoms and molecules present over here, then the chances of infraction would be high, and ultimately the absorption of light would be high. Also, we have this absorbance directly proportional to L. L is known as the path length. For example, if we have a sample tube which is very thin, the path length is very small, there will be less molecules present here to interact with the light, resulting into low level of absorption. But if we have a sample tube which is wide enough, there will be more molecules present in front of the light path, there will be more interaction, and ultimately the absorption of light would be high. Therefore, the absorbance is directly proportional to the concentration as well as to the path length, and if we combine these two, this absorbance is proportional to C into L, and finally when we remove the proportionality sign, we put a constant epsilon. So here A is absorbance, again C is concentration, L is the path length, and this epsilon, this constant, is the molar absorptivity, and this molar absorptivity is basically a characteristic value depending upon the type of sample. So for different sample, the value of molar absorptivity changes. This shows you that how electrons are being promoted. For example, we are giving energy in the form of light. So photons are there. This is an electromagnetic radiation. They are, when they fall upon a sample, the atoms and molecules absorb energy, the electrons are promoted. And now you can see the electrons are promoted. For example, they are promoted to maybe E1 level or E2 or E3 or E4. Now they are coming back. The absorption spectrum is mainly related to the absorption of light, not to the emission of light. Because when they come back, they will emit energy. But we are not concerned with this emission of energy, because right now we are focusing on absorption spectroscopy. And absorption spectroscopy is only limited to the absorption of light causing excitation of electron. That's it. We are not bothered about the electrons coming back and emitting light. For that, we'll focus on emission spectroscopy. So now in this graph, in this figure, you can see when electrons are excited from E naught to E1, since these two energy levels are close, the energy requirement for this is also close. As electrons are promoted from ground level to E2 level or to E3 level, since the energy gap is high, the light radiation absorbs are of shorter wavelength, because wavelength is inversely proportional to energy, or I should say, because E is hc by lambda, so energy is inversely proportional to lambda. So for example, if I mean if among two energy levels the gap of energy is high, then light of higher energy is needed. And what does that mean? Light of higher energy means a light radiation of lower wavelengths. And whenever the two energy levels are close to each other, it means that the energy gap is small. So the light radiation of a small energy is needed, and small energy corresponds to longer wavelength, because they are inversely proportional to each other. So in that case, if the levels are closer, we have a wavelength of we have a longer wavelength light to be absorbed. So in case from E0 to E1, the light radiation required is of longer lambda. If we compare it for E0 to E2, then we have higher energy, so shorter lambda. So for E naught to E1, since the energy levels are close, we need a light radiation of lower energy and longer wavelength, means longer wave lambda. And if it is happening from E naught to E2, since the energy gap is high comparatively to E1, since the energy gap from E0 to E2 is high as compared to the energy gap of E0 to E1, so we have here in this case we need light radiation of higher energy. That means we need a light radiation of shorter wavelengths. So in this way we can identify, or we can at least get an idea about whether a lower wavelength light is needed for absorption, or a higher wavelength light means lower energy light is needed for absorption. Now the main components of absorption spectroscopy: in each and every spectroscopic technique, the instrumentation is very important, which means the different components that are required for that spectroscopic study. In case of absorption spectroscopy, the major components, although there are some minor components as well, but the major components are the following. First is the light source, because we need a light source to excite the atoms and molecules present in the sample so that the electrons will be promoted. So light source is one of the most important component. Then we have a monochromator. The purpose of monochromator is to select a light of particular wavelength. This monochromator is basically a combination of a grating, which is used to split the light, or if grating is not available, we can also use a prism, because this prism can be used to disperse light into different colors, or the same work can be done by a grating is just like a saw. When light falls, it can be distributed into different colors. And then we have a slit. So a monochromator is basically a combination of a grating or prism along with a slit. Then we have a sample tube or cuvette. It may be made of glass or maybe quartz. Then finally the most important, the detector, which basically detects the absorbed, which then finally we have detector, which basically detects the transmitted light, and it also helps us to identify the wavelength that are missing in that continuous spectrum of transmitted light. And finally the readout device, this is basically the computer or our display system. These are the main components. We'll discuss each and every component in detail in the later part of this unit. So this is a flow chart representing an absorption spectroscopy. We have a light source that passes, which creates light radiation that passes through a monochromator, which select a particular color. Mono means one and chromator means color. It select a light of particular wavelength. Then this monochromatic light passes through the sample where interaction of the light with atoms and molecules takes place. Absorption will be done. Absorption will occur, and finally the transmitted light falls on the detector. We have a detector. We have a detector here, and then finally this detector detects the uh, transmitted light and identify the missing wavelengths, and they are being displayed in the form of a spectrum in the readout device or the computer. Now comes the principle of emission spectroscopy. So in emission spectroscopy, as I said before, we do not need a light source. Atoms here are excited by some other energy source where we need thermal energy to excite these atoms, and thermal energy can be obtained by either direct heating in a flame or by using a plasma, which is the fourth state of matter, and it is of very high energy, or using an electric spark on an electric arc. These are the few possible ways of providing energy, high energy to the sample, so that its atom and molecules will absorb energy and they transfer the electron from ground level to the excited level. Now when these electron comes back and relax to the ground state, they emit energy, because by emitting energy only they comes back to the ground state, and when they come back, the light that is emitted creates an emission spectrum. So in this case we are least concerned about the absorption, because here absorption of light is not taking place, rather absorption of energy in the form of heat is taking place, and light is emitted when electrons comes back from the excited state, for example this E1 state, to E0 state, ground state, and the light that is being emitted is then detected by a detector. Same detector is used as in case of an absorption spectroscopy. For example, most of the time we prefer using PMT, photomultiplier tubes. So the same type of photomultiplier tube can be used in absorption spectroscopy or emission spectroscopy. In case of absorption spectroscopy, as I said, the absorbance of light is governed by the Beer-Lambert's law, which is epsilon, C and L. Here in case of emission spectroscopy, the intensity of emission is proportional to N and A to 1. This I is the intensity of emitted light, N is the number of excited atom, and number of excited atom depends upon, of course, depends upon the concentration of the sample and also upon the energy, the thermal energy that we are providing to this sample by flame or a plasma or arc. And this 8 is represents the transition probability, because not all those transitions result into the emission of light. Sometimes an excited atom transfers its energy to some other atom. Sometimes it may also happen that it may come back without emitting light, just by emitting some amount of heat. There is also this is also a possibility. So not all types of promotions of electrons or excitations result into the emission of light, and therefore there is a term of transition probability that has to be considered in this formula to get the actual value of the intensity of light that are being emitted when the electrons fall back from the excited state to the ground state. So here you can see in this figure that when electrons are coming back from excited state to the ground state, some photons are emitted, means some light is emitted, because light is nothing but packets of energy which are called as photons. Again, emission spectroscopy, instrumentation, the main components are here. We do not need a light source, so there is no mention of light source here, while in case of absorption spectroscopy the most important component was the light source, and it was written at the first place, light source. Here we do not need a light source. Then the main source of excitation is the heating source, which may be any of these, flame or plasma or arc, etc. Then again we use a monochromator grating to select particular wavelength of light. Then we have detector, and again signal processor and display. This is our computer. And signal processor, we basically an amplifier is used. The purpose of this amplifier is to amplify the signal. So what is happening in case of emission spectroscopy? The light emitted is of very low intensity, and that low intensity is quite difficult to read, and therefore once it is read, it is the signal is amplified, and therefore the signal is, since in emission spectroscopy the light intensity is very low, therefore we use an amplifier which amplify the signal, and that amplified signal is displayed on the computer for easy understanding of the user. This is a flow chart showing with sample, and since in excitation, since in emission spectroscopy we do not use a liquid sample, we use an aerosol of sample, because if the sample is in liquid state, exciting those atoms and molecules becomes a bit difficult. And for example, if you have a liquid sample and you are directly introducing that liquid into a flame, it may cause that flame to extinguish, it may lower the temperature. Therefore, instead of taking sample in liquid form, we convert it into aerosol, and for that we have a sample that is being mixed with fuel and oxidant so that it gets converted into an aerosol. Just like the perfume we are using, we have a liquid fragrance and alcohol is there, then it mixed with air and it then converted in the form of an aerosol. A similar aerosol is being injected here, and then we use a flame, we use a thermal energy here, we use thermal energy, either flame or spark, which heats this sample and convert the atoms present in aerosol into vaporized atom and excited atom. Those excited atoms, when returned, they emit light of particular wavelength, and finally that light is detected by our detector and displayed on the readout device. So this is a flow sheet of emission spectrum. We'll discuss all these components, individual components, in detail. Then, just like a concluding remark, that atomic spectroscopy is mainly divided into two types: the atomic absorption and atomic emission spectroscopy. In atomic absorption spectroscopy, light of is in atomic absorption spectroscopy, light of a specific wavelength is being generated by a light source like a hollow cathode lamp, which is used as a light source. This light source excite the electrons. This light source excite the atoms present in the sample, and its electrons are excited to the higher level. These are the higher levels, E naught. Then we have E1, and this the third one is E2, and this is E1, and we have E naught. So this causes the electrons to be promoted to higher levels from ground level. This is E0, then we have E1, we have E2, and then we have E3. The electrons are promoted to these levels, and during this promotion they absorb light of characteristic wavelength. That light corresponds to the, each and every atom has a different characteristic wavelength, so a particular wavelength of light corresponds to a particular atom or a particular group of atoms. Therefore, here it is written that light of specific characteristic wavelength is absorbed, which causes the promotion of electron from ground state to excited state. This is called as excitation or absorption. And this absorption is proportional to the elemental concentration. Therefore, we can use this technique for quantitative analysis as well. The wavelength gives us an idea about the quality of the sample, means the type of sample, the structure of the sample, the nature of the sample, while the amount of absorption, the intensity of transmitted light, because if the absorption will be higher, intensity of transmitted light will be lower. So the amount of absorption the gives us an idea about the concentration of the sample. So these two techniques can be used for qualitative and quantitative analysis. Quantitative means the amount or concentration of the sample. while qualitative means the nature of sample, its structure, and the group it belongs to, whether it is an alcoholic sample or an acid or an aliphatic compound and aromatic compounds. So by using this technique, we can have all these information. Then we have atomic emission spectroscopy. And in atomic emission spectroscopy, we do not need a light source. So we uh, uh, so in emission spectroscopy, we need a heat source which is provided by a flame or a plasma, and then this heat source causes the atoms to excite and their electrons are promoted to next higher level. From here, the electrons, upon absorbing energy in the form of heat, they are promoted to next level, and when they return back, they emit light, because in this excited state they are having higher energy. They want to relax, they want to come back to the ground state, and for that they have to emit energy, they have to release energy to come back to their original state. So they emit light and come back. When they emit light, this light is basically the basis of emission spectrum. This light is read by the detecting device and an emission spectrum is generated. So here the excitation depends upon the energy that we are giving from an external source, and again the intensity of absorption, and again the intensity of the emitted light is proportional to the concentration or the elemental concentration of the sample. So this technique can also be used for the quantitative as well as qualitative analysis, because the wavelength at which the lights are emitted, they basically corresponds to the nature of the sample, its type, and its structure is also related to that wavelength, and the intensity of that wavelength corresponds to the amount of sample, or I should say the concentration of the sample. So this is all about the basics of spectroscopy and the basics of absorption and emission spectroscopy. So I hope that in this class you have learned about the term spectroscopy and how we can differentiate between atomic absorption and atomic emission spectroscopy, because most of the times students get confused about the absorption, about the term absorption and emission spectroscopy. Most of the time students think that even in emission spectroscopy we use a light source, and that light source causes excitation, and when the electrons come back they emit light. But this is not the case. In emission spectroscopy, we do not excite the electrons with the help of incident light radiation. Rather, we excite the electrons by using thermal energy. On the other hand, in case of absorption spectroscopy, we are only concerned with the absorption of light, and that absorption occur when a light radiation from external source is when a light radiation from external source falls on the sample, and there will be some interaction with the atoms and molecules which causes the absorption. So this is all about, and we'll be discussing more in the next few classes. Thank you very much.